So you just purchased an electric vehicle, or you're planning on purchasing an electric vehicle, and you are trying to determine whether or not you need some sort of automatic shut-off system to prevent main service overload. And it could be for a Tesla EV charger or a EV charger from another manufacturer. So there's a couple of reasons you may want to do this. So first is if the amperage you want on the EV charger plus the amperage on your main electrical service that it generally sees will likely trip the main breaker. So let's say your current capacity on your electrical service is 80% of the breaker rating, and then you add a Tesla charger. Let's say you want to maximize it to make the charging as quick as possible. So let's say you get a 60 amp charging capacity from the EV charger. And that 60 plus the normal amperage that you normally use in the house exceeds that main breaker. The main breaker will trip and it will basically shut off the power to your entire house. And then you would have to go downstairs and manually trip the breaker back on. And that would be an inconvenience. So in that case, you may want to provide a automatic shut off system to automatically, shut off the EV charger so the main breaker does not trip. And then when the power goes back down, the system would sense that and then automatically turn the power back on to the EV charger. Another reason is, some condos and co-op boards want the tenants to limit load to each unit to prevent overloading the main electrical service. Because if they were to increase the main service, that would cost a lot of money for the building, and that's something that they may want to avoid doing. And I'm a licensed engineer in New York State, and I've done a few jobs for clients from condo or co-ops that required a letter as well as a set of plans from an engineer to show a system that can basically limit the electrical usage to a tenant that wanted to install an EV charger, just so that there was some sort of proof that they wouldn't be increasing the electrical service into the building by installing this EV charger. And this is the first time I learned about these automatic shut-off systems. And sometimes these systems are referred to as energy management systems. All right, so before I start talking about this energy management system, I just want to go over the basics of some of the EV chargers that are out there for the Tesla. So the Tesla, they have a lower, cheaper version. It's the mobile connector. It's priced at about $250 the last time I checked. And it basically looks like this. This is the charger. You have some sort of adapter piece that plugs into a receptacle. So whatever receptacle you have, they have various different types of adapters that would fit the receptacle that you need to plug it into. And then this adapter piece will plug into this. And then this is basically the charger that goes into your EV car. So it goes up to 3 miles per hour charge. It's about 1.3 kilowatts. Up to 30 miles an hour on a higher charge at a higher voltage of 240. And on average, a Tesla battery provides about 330 miles. So if you just generally look at these numbers, again, they're not perfect, but it's an average. You have, with this charging capacity, you need 110 hours of charge to fully charge the battery. That's a pretty slow time. And with this 30 miles an hour, it's going to be 11 hours. So, that's a little bit more reasonable. And these are some of the adapter parts that can be purchased based on your outlet type. And the outlet types are based in NEMA ratings. These are just standard ratings, which is the National Electrical Manufacturers Association standard. And again, this adapter piece, basically this part plugs into this Tesla charger right here. And these are some of the adapters that are available. You can get the NEMA 515. Again, the second number is the amperage rating, so it's 15 amps. And the first part just represents the type of receptacle it is. So on 120 volts, the NEMA rating starts with a 5, and for the 240 volt at the higher voltage, the NEMA ratings can be any one of these. So it starts with 14, 6, or 10. This is the other part right here, and this is again another 120 volt. So on the lower voltage, they come with 15 or 20 amp, and at the higher voltage, they basically come in 15, 20, 30, or 50 amp. And the currents are basically 80% of this amp rating. So if you have 20, 80% will be 16, and that's how these currents are calculated based on this. But for the 50, 80% would be 40 amps. So in this case, it's a little bit less than 80%. So I'm just going to go over some of the NEMA ratings just so you kind of understand what they mean. So if you look on the left here, these are the charts for the different NEMA ratings. So the NEMA ratings are in this column right here. And you can see for the NEMA 5, it's basically right here. It's a 120 volt rating. And this is the standard receptacle that you see on walls that you plug standard appliances into. So those are basically the NEMA 5 rated. And you can see the R for receptacle, P for the plug. And this is generally what the NEMA 5 look like. And you can get in 15 or 20 amperes. Now you can have a NEMA 1450 adapter, and these are typical for electric clothes dryers. So if you look down here, this is the NEMA 14, and they're rated for 120 volt, 125 slash 250 volts. Okay, so there's two ratings here because if you look at the shape of it, let's look at the NEMA 50, for example, this one here. You can see that there's a ground, which is here. And then you have a W, which stands for white. So this is probably the neutral. I'm not 100% sure, but one of these three are the neutral, and the other two are the 120 volt hot legs. So one hot leg and the neutral would make the 125 volts. And then the two hot legs would make the 250 volt out of this rating here. So that's why you see two of these ratings. And then you have a G, which is the ground. So that's what these NEMA ratings would look like. And you can see the available adapters available. They have the adapters for the 520, the 515. They even have it for the 6s. And the 6s are just a 250 volt rating. Without the 125 volt here, as shown in the NEMA 14. It's just a 250 volt rated receptacle. And these are the plugs, right? So if you have this type of receptacle, you would have to purchase this type of adapter to fit that NEMA 6 rating. And for these, you could see that there's one that's rated a 10. And a 10 is similar to the 14, except it does not have a ground. So if you look here, it's the same thing as the 14. It's 125 slash 250. But if you look here, there is no ground. So if you look, for instance, this one, it's a 30 amp. And if you look at 30 amp column here, you can see that this one has a ground, the NEMA 14s, but the NEMA 10s do not have that ground. So that's the difference. So when you purchase the adapter, you just have to make sure that you get the correct rating so that it fits the outlet that you have or you're planning on installing for this EV charger. Okay, now that we talked about the Tesla mobile connector, they also have a wall connector, which is priced a little bit higher at about $450 last time I checked. So the wall connector, as opposed to the mobile connector, the wall connector looks like this. It's a little bit more permanent than the mobile connector. And these charge a little bit higher at 44 miles per hour at a higher kilowatt charging rate. And they can also be rated for the NEMA R. NEMA R just stands for, it's rated for the outdoors where it could be raining or snowing. And they come in these standard sizes here. So it goes from 15 all the way up to 60 amps at a 240 volt power. There are different ways you can install it, whether from the top, the bottom, left or right, as shown here. In this picture, it's installed from the bottom. As you can see, the electrical conduit is coming up from this way. So there's some flexibility in how to install it. And here's another chart showing the circuit breaker ratings here. The maximum output, again, it's just 80% of the circuit breaker rating. And they're all at a 240 volts rating. And here is the charge speed based on the models here. So you could see you could get a maximum charge speed of 44 from this list, but it's going to vary depending on the model type. So looking at these numbers, let's just go with this 44 miles per hour charge. If the typical full battery charge range, just an average, is about 330 miles, at 44 miles of range per hour charge, you're basically charging it full in about 7.5 hours. So this is more a reasonable charging rate, I think, and I think everybody wants to charge it at the highest rate possible. So let's say you want to get that maximum 60 amp EV charging capacity, or your 60 amp EV breaker size, and your main electrical service is, let's say, at 120 amps. So that's your main breaker size. And let's say under normal conditions, you have a high electrical load, let's say 100 amps, because, for example, you might have electric cooking or electric water heater. So if you have 100 amps normal load and the EV charger is 60 amp rated, which means you're only pulling 80% to charge the electric vehicle. So 80% of 60 is 48 amps. So you have 48 plus the, let's say, 100 amp normal usage from your home appliances. That's going to give you 148 amps. And your main breaker in this example is 120. So your EV charger being on can trip your main breaker during normal usage. So in this case, we will need the automatic shut-off system or the energy management system. And the one I'm going to be discussing is DCC, which is by RVE. And this is their model for an electric vehicle energy manager. And this is the one that I actually installed for my Tesla. And I've had it for about 2 years now, and I've had no issues, and it works exactly as intended. I can tell you that it works for me. So this is the actual box. It looks like this, and you could kind of see the approximate size of the unit. And this is a picture of another installation of it. So the box is right here. This is where the switching occurs. And then you could see the conduit will connect the electric wiring to this charger. And the way it works is it monitors the amps in the main feeder and automatically turns off the EV charger once it reaches 80% of the main breaker fuse size. And then if the amp in the main feeder stays below 80% of the main breaker fuse size for 15 minutes, I think there are different settings within the equipment, but 15 is one of them, then it'll automatically restore power back to the EV charger. So I'm going to start talking about the DCC, and I'm going to start with the DCC-9. There's actually 4 versions. There's a 9, 10, 11, and 12, but I'm going to start with this 9 first. And if you look here, this is the DCC right here. And this is your meter. So the service comes in through the meter. It goes through the main disconnect. This is a 240 volt rated system. It goes in, and you can see a white wire, which is the neutral. You have the red, which is a 120 volt hot leg, and then you have the black, which is the other 120 volt hot leg. And you can see it runs through this circular object, and this is the current transformer that basically senses the current that's going through the wire. And the way it works is by monitoring the electromagnetic field that that current generates. So you have two of these that are monitoring the amps within each of the hot legs. And the signal from this current transformer is then basically controlling this relay right here that will switch the power from the EV back to the main. So this is the EV charger, and it goes right to this EV charger right here. And then the power internally will split into the relay, which then goes to your EV charger. And then it basically, the main feeder goes right to your main panel right here. So this is the actual picture of the internals of the box. And you could see that the relay is right here. And the relay is what switches the power from the EV back to the main service. And then here is the EV charger breaker right here. And when selecting the model number for the DCC9, you have to select it so that it's a maximum of 50% of the main power supply over current protection device. So if you have an 80, for example, the max has to be 50% of that. So the max has to be 40. So you can see that that is allowed. And you can obviously go a little bit higher because 50% of 100 is 50. And since that's the max, a 40 amp would work. So you could see that the higher the power supply, it's all allowed, as you can see here. But at the lowest, it's going to be 50%. So here, 50% of 60 would be 30. Same with 100. And with this one, they use a 125 because I believe a 120 is not a standard size. So they go with 125. So the 60 would work in that case. All right, so now I'm going to go to the next one, which is the DCC10. So as you can see here, it's not actually in line with the main service, just like in this case, you see it's in line with the main service. For the DCC10, it's actually off to the side and it gets connected. So it's not in line to this, it's actually to the side and it's being powered through a breaker in the panel. So you can see the power goes to the relay, which basically will switch the power to the EV or basically disconnect the EV power so that all the power could flow through the main. And again, it is measuring the current with these current transformers at the main right before it splits between the EV and all the other loads on the main panel. So that's the slight difference between the 10 and the 9. And in this case, the 10 does have a circuit breaker for the EV charger. And the internals of this box looks like this. You do not see the CT inside, just like in the 9. So you can see the CTs are right here in the 9, but in the 10, the CT is not inside the box, it's actually off to the side. And it comes with a wire, so basically you would attach the current transformer to the main and then run the wires from the CT to the box so that it can measure remotely the amperage. And here are the amperages that this box comes with. So it comes in 30, 40, 50, and 60 amps. And it goes up to a main power supply of 200 amps, which is similar to the DCC9. But the DCC9 only goes up to the 125 amps. And if you wanted to go up to the 150 and 200, you would have to go with a DCC11. So that is the difference between the 9 and the 11. And that's just with the rating. So DCC11 can handle 150 and 200. And the 9 handles the rest here. So that's the only difference between the two. And here's another installation example for the DCC-10. You can have it in this type of configuration as well. Basically, it taps off not basically from the actual disconnect, but it taps off of the main going out with these piercing connectors that basically will tap into the main and then run in exactly to this. And then from the relay, it basically will go to the circuit breaker. And when you do these installations, these are just a typical diagram, but you have to follow your local electrical codes to see if these type of installations are allowed in your local area. And you have to follow all the NEC codes as well as the local codes dealing with the location that you are installing this system at. So the DCC-11 again looks like this. We just covered it. It's very similar to the DCC-9, except that the amperage for this is higher than the DCC-9. And again, it's very similar installation. It's in series to the main feeder right here into the panel. And the rating is higher than the 9. It goes 150 amps to 200 amps, and the DCC-9 is 125 and down, as listed here. So the DCC-11, here's another wiring diagram showing the internal components. So basically the line, this is your main power source. So you have 120 volt through here, through the CT, the other 120 volt through this CT, and then you have a neutral wire as well. And this all goes through to your normal load. And then within the box, you could see that it splits off, and one goes basically to your power relays here, which will basically open and close the circuit to your EV charger. And then some of the power from the main, it goes into a transformer that basically converts the voltage to a low voltage for your control wiring. And then your CT basically takes the amp reading and basically sends it to the circuit board where the amperage is read. And you can also have connections to energy management systems if you like, to monitor what is happening within this box. So for the DCC-12, it's very similar to the DCC-10, except that there is no breaker within the DCC-12 for the EV charger. Okay, and the amp ratings are listed here. It goes up to 200 amps, and an EV charger rating of 30, 40, 50, and 60 amps. And you basically place it such as this. These are just two examples of how to install this box. You can have a breaker that feeds into this, and then it basically goes through this to your EV charger. You can also have some sort of configuration like this where it is off a sub panel that is coming off the main. And in this case, you have to be a little bit careful, and when you calculate the main demand to your meter with the EV charger, you still want to make sure that it falls underneath the main overcurrent protection device. So what this means is, let's say your demand is more like 50 amps for this, even though the main is at 100 amps. This is just an example I'm just giving just to show some numbers. And let's say your demand is 50 here. So 250s will kind of fall under this 100 amp main breaker size. But if your DCC-12 can handle basically up to 80% of the load to the sub panel before it disconnects the EV charger, that 80% is more than this 50 amp demand. All right, you're going to be at 80 amps, which is 30 amps over. And if you're 30 amps over plus this 50, it's basically 80 total here plus 50. It's 130 amps, and that'll open up your main breaker and shut off the power to this entire system. So with this type of configuration, you have to include the EV charger and just confirm that even with this charger, the electrical demand will still be under the main overcurrent protection device in your main. And here is the internal wiring diagram of the DCC-12. So this is very similar to the DCC-10, except that the breaker for the EV charger is not part of the box. All right, all you have is the relay and your remote CTs right here, the current transformers, and it'll basically disconnect the power to the electric charger. So the only difference is there is no circuit breaker for the electric charger in the 12 compared to the 10. And with these boxes, there's an adjustment that you can make using dip switches. So you can actually change the trip percentage from that 80% default to 60 or 70% if you'd like. And also there's a 15-minute delay. So if it senses the current is below that threshold that is set here under the trip percentage for a given amount of time, then it'll basically switch the power back to the EV charger. And that default is the 15 minutes here. And the EV charger breaker has to be set at an amperage that is 50% of your main power. So if let's say your main power is 100 amps, you have to set the dip switches so that it's half of that, so 50. So it would have to be in this sort of configuration here. So if we were at, let's say, 80 amp main power supply, then you would have to adjust the dip switches to be in this pattern right here for a 40 amp. And when I was installing my DCC-12, this is the one I have, when I didn't do it at 50%, the system didn't work. So I think that you have to set at 50% for the system to actually work. All right, so I want to show you some examples of different configurations that I believe are most common. So for this one, I'm going to start with this. This would be for, let's say, a condo or co-op building. And let's say you have the service that's coming underground, which is typically in New York City. So it's in the cellar. So basically running under the street, under the sidewalk. It comes into the building, into a box called the service end box. And this is where the utility company will make connections to the wiring that's the property of the tenant. Then it goes into their meter, and it goes into their disconnect. In this example, it's a 200 amp rated fuse disconnect. All right, and the fuse is at 200 amps. And it goes in and it goes up to the tenant's panel, which in this example is the second floor, but it could be on the 30th floor or any other floor. So to get a circuit from this panel to the EV charger is not very ideal. It's too far. So you would basically use a system like this, where you provide a separate local fuse disconnect switch. In this example, it's going to a 60 amp EV charger. So the fuse is going to be at 60. And the part we're using is the DCC-12. And it goes to your EV charger, which can be close to this location or it could be hundreds of feet away. It doesn't matter. If it's more than 100 feet, you may have to size the wiring a little bit higher to account for some voltage drops from the long length of wiring. So in this example, we have a DCC-12, so at 80% of the main disconnect, so that's going to be at 160 amps, it's going to disconnect the power to the EV charger, sending all the power to your main panel. And let's say under normal usage, you have 100 amps. That means that under normal usage plus the 60, it will basically trip this DCC-12. But if your normal usage is at 100, you may not even need a system to disconnect the EV charger because your total is 160 amps, which is still less than your main disconnect, and it won't even trip your main disconnect during normal operation. So in those cases, you don't even need this type of system. The only time you need it is if during normal usage, such as in my case, I have an electric water heater, and with the AC system on full, so basically all the AC systems on, my load was somewhere around 160 or more. So with the EV charger at 60, I was exceeding the main disconnect. So in cases like that, these type of systems would be good to have. So you have to see if you actually need the system before you purchase and install one. So this is one case. The other case, you might have a system like this in a multifamily condo or co-op building where you have a meter bank. So you have one main disconnect that will send power to the meter bank, and from here it goes to the individual tenants. And a meter bank looks basically something like this. And in this example, these are the breakers for each of the meters. So you can see each meter has their own breaker that then serves the feeder to the tenant's panel. So in that case, you install it a very similar way. But in this case, the only difference is the CT is in the meter bank, basically around the feeders going to that tenant. In this case, the CT was in the disconnect that was going up to the tenant's panel. So uh, in these situations, the wiring is going to be sized based on the NEC, and I show it here. But basically, to do that, I'm just going to run through one example, not so that you install the wiring yourself, but to check the wiring that was done by the licensed electrician. All right, you need to make sure that you hire a licensed electrician to do this work. And I'm just showing you this just to see if their work was done properly. So to size the wiring and the conduit size, you have to use the NEC table. So for example, let's look at this one. If it's a 60 amp fuse, you go here, and this is the column that I typically use, the higher Fahrenheit. So basically this one, it allows for higher amperage. And for a 60 amp, you can see that it falls within this one here. So this number 6 wire can handle up to 75 amps. So you can use a 6 AWG wire size. And as you can see, the wire size is, as the wires go down, the numbers go down. It's actually a thicker wire, right? That's why as the numbers go down, you can handle a higher amperage. As you can tell in this column, the amperage is going up. So you have a 6 in that case, and a number 10 ground. And to size the ground, you use this table here, where if it's a 60 amp breaker and you want to use copper, generally that's better to use. You need a number 10 AWG size wire ground. So that's how you size the ground, and you have to size the conduit size next. So there's going to be two number 6 and one number 10. The 6 is larger, so I'm just going to assume that we have 3 number 6s. And when you go to this table to size the conduit, there's 2 charts, one for EMT tubing and one for RMC. Generally, they're about the same, but I put them both here just so you could compare. And for number 6, 3 of them would fall under here, up to 4 conductors, and that's a 3/4 inch size. So that's why if you look here, it's going to be a 3/4 inch. So for this 60 amp, you need something like this, okay? And this is generally what you should see installed. Now for this, for a 50 amp, it's going to be a little bit different. The wire size can be a little bit smaller. So it's going to be an 8 rather than a 6, right? And because the higher the number, the smaller the wire. It works the opposite way than the number size. So as you get higher, the number, the wire gets smaller. So in this case, for a 50 amp, the wiring decreased to an 8, and then you can use a 1/2 inch conduit in that case. And again, these wire sizes are not there, so you can install this system. You should always hire a licensed electrician to do this work. And this is here, so you can see generally what should be installed. Okay, now in these two diagrams here, these are most likely the case for a single family home. So let's start with this one here, where the service comes in underground in the cellar, and you have a meter, and then you have your main disconnect in the panel itself, and then it goes out to your loads wherever they may be. And this one, since everything is very close together, you can actually use the breaker in the panel to feed your DCC12 rather than installing a separate disconnect in this case, because the circuit breaker in the panel is very far away from the actual DCC12. Also, in this case, your circuit breaker may be on the 20th floor, and that run may be very long and difficult to install to your DCC12, which is why you need a separate disconnect, such as drawn here. So in this case, for a simple one-family home, everything is kind of close. So you could use this breaker to feed your DCC12, and then your remote current transformer should go right on the main before it splits to your main loads and your EV load. So this is one way. Another configuration, which is very similar to this, except the meter is on the outside. So some homes will have an installation such as this, where it comes in overhead, right? So not underground, and it goes through this mast, and it goes to a meter outside, or it can also be inside the house, and it goes right into the main circuit breaker, and then everything else will be identical to this example we just discussed here. So you can use the breaker within the panel to feed the DCC12. And in these four examples here, I only talked about the DCC12. So I'm going to talk about the DCC9 and 11. Okay, so these are the ones where it's kind of in series to the main feeder rather than off to the side, and where you provide a separate feed to the EV charger, such as in these cases here. You see that it's a separate feed into the box rather than in series or in line to the main. So when you install these 9 and 11 boxes, it's in series to the main, so it's in line. And then from here, internally, there's a separate breaker to your EV charger. So you can install something like this. But in this case, I prefer to use the DCC12 just because the 9 and 11, if you were to maintain, if you had to fix this device or replace it for whatever reason, you now have to shut off the main, which then shuts off your entire electrical system. So basically, during that work, all the power to your entire house will be off. So it's not a very ideal case. So that's one of the reasons I prefer not to use the 9 or the 11. Now, in a similar case where you have, rather than the main disconnect here, you only have the disconnect within the actual panel. So in this case, that's the main difference. And with the 9 and 11 installed like this, I again wouldn't prefer this situation because it's not clear if these boxes are rated for service installations. So if it's on the service, it has to be rated for service equipment, and I'm not sure if these are. If you were to do some maintenance work on this system, then how would you shut it off? There is no main disconnect here, like in this example. So to cut off power, so you can do some sort of repair work on this or just replace it, you would have to ask the utility company to shut off the power. And they're usually not very quick. So that might take a little bit of time and it might not be a very ideal situation. So I wouldn't recommend installing the 9 or 11. And I prefer the installation of the DCC12 just because you can separately shut off the DCC12 if you had to do some sort of repair or replacement work without having to cut off power to anything else. You could just isolate the DCC12 since it is on its own separate disconnect. Same as with this example here, it's on a separate disconnect. Same with this, as well as here as well. So I would basically recommend installing the DCC12 in any one of these 4 configurations here, based on whichever one is most similar to the electrical service at your project location. So I wanted to bring up some similar products from different manufacturers so you have some options to choose from. So there's a company that makes this called a BlackBox, and it's very similar to the DCC model that I just described in this video. The price point of these are $686 and this one's $671. And the price point for the DCCs were about the same. I think it might be a little bit more at around $700 or $800, which is the price that I saw when I last checked. So you can also look at this product, the BlackBox, very similar to the DCC. And again, it does pretty much the same thing. It monitors the main feeder and automatically turns off the EV charger if it reaches above a certain threshold. And then when the threshold, when the amps go below the threshold, it'll basically restore the power to the EV. They also make these splitter boxes. So this company is NeoCharge, and they make a product where you could plug it into, let's say, an outlet for an electric dryer, and it basically splits it. So you can have the electric dryer on one outlet, and on the other outlet, it'll go to your EV charger. So there's different model types based on the outlet type that you have available. So you could see which one's available, and you would select the proper one to install. And you should make sure that the outlet matches the plug for your EV charger before you purchase one of these. Also, this looks like it has to be located very close to your EV charger location. Otherwise, this might not work. So you might have to kind of see how far your EV charger is and whether or not, if you install one of these, the EV charger will reach your car and also reach this outlet plug. But this looks like a very simple installation if everything is available at your location and everything is close to your EV charger location as well. Again, it does the same thing. It just basically splits it depending on the load. So if your appliance is on, it'll basically switch the power off to your EV, and it'll send the power to your appliance. And then when your appliance is off, it'll switch the power back to your EV charger automatically. So I will leave the link for all these different model numbers that I discussed in this video down below. So you could click on those links if you like. So if you like this content, please subscribe so that you could be notified next time new videos are uploaded. Thanks for watching.